Hey, and welcome to The Explainer. Sometimes a single idea, just a thought experiment, can totally flip our understanding of the universe on its head. And that's exactly what we're talking about today, Galilean relativity. So, let me ask you something right off the bat. Are you moving right now? I mean, really think about it. You probably feel like you're sitting still, right? But the Earth is spinning, hurtling around the sun, and our entire solar system is zooming through the galaxy. So, are you really still? It's a trickier question than it sounds, and the answer is, well, it's complicated. And to untangle that complication, we've got to travel back in time. We're going to the 17th century to meet the man himself, Galileo Galilei. He laid out this incredible thought experiment in his big book, the Dialogo sopra I due massimi sistemi del mondo. Okay, so here's the setup he proposed. Picture this. You're locked in a cabin, way down below the deck of a big ship. No windows, no portholes. And the ship is sailing on perfectly calm water, so smooth you can't feel any bumps or swaying. Now here's Galileo's big question. Is there any experiment you could possibly do inside that room? Anything at all that would tell you whether the ship is moving or if it's just tied up at the dock, completely still. Now, to solve Galileo's puzzle, we actually need to take a quick detour. We have to grasp this one really fundamental rule about how the universe works. It's a law that applies to, well, everything, from an astronaut just floating in space to a hockey puck gliding across the ice. It's called the principle of inertia, and honestly, the best way to think about it is like the universe's official law of laziness. Basically, things just keep doing whatever they're already doing. If an object is sitting still, it's going to stay still. If it's moving in a nice straight line, it's going to keep doing that. The only thing that changes this is an outside force, a push or a pull. It's so basic, so important, it's also called the primo principio della dinamica, the first law of dynamics. So this law of laziness, inertia, it works like a charm inside something that physicists have a fancy name for, an inertial reference frame. Don't let the name scare you. All it means is a point of view, a sistema di riferimento inerziale, that isn't accelerating. It's not speeding up, not slowing down, and not turning. Kind of like our perfectly, smoothly sailing ship. That's our ideal inertial frame. Okay, so now that we've got these tools in our pocket, inertia and the whole idea of an inertial reference frame, we can head back to Galileo's windowless cabin and see what he figured out. All right, let's do some experiments inside the cabin. First, imagine the ship is docked. You drop a ball. Where does it go? Straight down, right to your feet. Simple. But now, here's the part that messes with your head. Let's say the ship is moving forward at a constant, smooth speed. You drop the ball again, and it lands in the exact same spot right at your feet. How is that possible? Well, think about it. When the ship is moving, it's not just the ship. You are moving with it. The air in the cabin is moving with it. The ball in your hand is moving with it. Everything inside that cabin shares the same forward motion, the same inertia. So from your perspective inside that room, it's as if nothing has changed at all.
And that realization, that is Galileo's great insight. It's the core of what we now call the principle of Galilean relativity. It means the basic laws of physics, the rules that govern how things move, are identical in any inertial reference frame. There's no special, correct viewpoint. There's no absolute standing still. All motion, as long as it's uniform, is relative.
But hold on a second. I can almost hear you thinking, wait, that can't be right. I can absolutely feel when I'm moving. When a car hits the gas, I feel it. When an elevator lurches, I feel it. And you're 100% correct. So what gives? What's the difference? Well, the key word was smooth. Let's see what happens when the rules bend a little. Yeah, that smooth, constant motion was the secret sauce. So what does happen if the boat suddenly speeds up, or slams on the brakes, or takes a sharp turn? In other words, what happens when you accelerate? Aha! This is when you can feel the motion. You're now in what we call a non-inertial frame. And in here, things get weird. The laws of physics seem to break. You know that feeling of being thrown back in your seat when a car accelerates hard, or being pushed to the side on a fast turn? Physicists call these forze apparenti, apparent forces. They're not real forces like gravity or a push from someone's hand. They're phantom forces that only show up because your point of view is accelerating. And these apparent forces can do some really strange things, like mess with your weight. Think about an elevator. As it accelerates upwards, you feel heavier for a second, right? Your peso apparente, or apparent weight, increases. And when it accelerates downwards fast, you get that stomach-lurching feeling of lightness in assenza di peso, or weightlessness. Your actual mass hasn't changed one bit. You're just experiencing the bizarre physics of an accelerating frame of reference. So you see, Galileo's idea was way more than just a cool thought puzzle about a ship. It was a foundational piece of physics. It set the stage for Newton, and hundreds of years later, even for Einstein's theories of relativity. It was an idea in motion that literally put science in motion. And Galileo didn't just stop at the concept. He gave us the math to back it up. He developed what we call the Trasformazioni di Galileo, or Galilean transformations. It's basically a mathematical recipe book. If you're on the shore and I'm on the ship, and you know how fast my ship is moving, you can use these transformations to perfectly calculate and predict what I'm seeing from your point of view. It's a way to translate physics between two different moving observers. And here's the really beautiful part of it all. The transformations show that while things like position and velocity are totally relative, they depend on who's doing the measuring, the laws of physics themselves are not. They are absolute. Newton's famous law, F equals ma, works just as well on a bullet train as it does in a quiet laboratory. The fundamental rules of the universe don't change just because you're moving. And believe it or not, this search for the perfect place to do physics is still going on today. I mean, think about it. Even the Earth is in a perfect inertial frame because it's spinning and orbiting. So modern astronomers use something called the International Celestial Reference System. It's a coordinate system that's essentially fixed against incredibly distant galaxies and quasars, the closest we can get to a truly still, non-accelerating frame of reference to test our laws. Which brings us right back to where we started. Galileo's genius was showing us that there's no special center of the universe, no absolute rest spot. All uniform motion is relative. So the next time you feel like you're sitting perfectly still, I want you to think about this. If everyone, everywhere, is just moving relative to everyone else, is anything, anywhere, truly standing still?